All right. So today I want to talk about how to characterize particles. So look at sizes and distributions, and I'll go over a few different ways of doing this, and hopefully, hopefully some of the machines you've seen already, maybe some you haven't, and we'll see how that goes then. So, an analogy to, kind of polymer chemistry. So you have a molecular size distribution or a molecular weight distribution. Obviously, if you make lots of particles, you'll have a particle size distribution. And you can then, if you have a distribution, you can calculate the average or the mean particle size. Now, so for example, I think you've seen this picture before. If you want particles to crystallize, and in this particular case you see an FCC colloidal crystal of polystyrene spheres, then obviously they all have to be roughly the same size. And then the dispersity over that typically has to be, definitely less than, 5 to 10%. If it's more, they simply won't crystallize. So for some applications, it's vital that you'll get really, really narrow particle size distributions. Other applications, it might even be better to have a broad particle size distributions. And then of course, we have to have ways of measuring this, and it's not always easy. So for example, the other system here, if you want to make a high solids dispersion in water, we know that monodispersed particles crystallize 74%, which means 26% of air or water left. Yeah. So that same particular system, if you would stir it, would jam at 64%. So basically, if you would have viscosity as function of volume fraction of particles at 64%, the viscosity goes to infinity. So it's basically a solid then. So if you want to make a dispersion that has higher solids, you have to start playing with the particle size distribution. So you can imagine, because you've got gaps in there, and we saw it before, that typically a gap between three particles in 2D would be 0.15 times the radius of the spheres that you've used. You can imagine that if you use different ratios of different particles, you could get this overall solids up, so it's still a liquid. So you can make liquid dispersions of 80%, 85%, and even pushing it even higher by playing with the particle size distribution. And not only synthesis is important then, but also, finding ways to establish that what you've made is actually the particle size distribution that you would like to have. So one of the things that's a little bit complex is you have lots of different ways of measuring it, and therefore you can calculate lots of different ways on how to calculate the average, in a way. So imagine, for example, 3 spheres, and then the diameters are just 1, 2, 3, in this case. Then the question is, the question you would ask yourself is, what is the average size? So the easiest way to do this is that you say, okay, I'm going to measure the diameters of these 3 things, and in this case would be like 1, 2, 3. I add them all up together, and I divide it by the number of particles that I have, in this case 3. So my average would be 2. And so that would be a good answer. But from mathematical terms, that would be the average diameter d and then a square bracket 1.0, because what you do is you measure the diameter and you divide it by the number of particles. Now there are different ways of calculating things. So for example, people that do catalysis, they're not really interested in the number of particles, they're more interested in the surface area. And with that particular respect, what they do is they calculate the surface, they use the surface area rather than the diameter to calculate the mean. So they do 1 to the power 2 plus 2 to the power 2 plus 3 to the power 2 and divide it by the total number of particles. And they come up with a different number. They come up with 2.16. So the number surface mean is D20 in this particular case. And then obviously you can think of lots of other ways that you get different averages that for different applications would be the average that you would like to use. So here, this big one looks a bit crazy at the top, but it's not too bad. In order to get these mean 1, 0, 3, 2, 4, 3, 5, 4, light scattering is a bit of a weird one here. I set 5, 4 here, that's an average one. For small particles, it would be 7, 6. because it's Rayleigh scattering, but we come back to that in a little bit. So this big equation there, all I want to get across is that there are lots of different ways to calculate the average. And obviously, if you want to compare one technique with another technique, you might have to interchange these numbers. So, because people, come up with a different number for the same set of particles if they use a different type of technology. So, okay. So, what type of techniques are there to measure particle size? And one of them, which is discovered a long time ago and which is used a lot, is measure the size with light scattering. Now, light scattering is not always easy. So for very small particles, if the particles are basically smaller than 10 times a tenth typically of the wavelength of light, you get a scattering profile like this on the left here. So you have quite an isotropic scattering distribution. So the light comes in, and this one particle reflects light. Depending on the angle, there's an angular dependence, but the back scattering is roughly the same as the forward one. So there's a symmetry there. And in order to solve then this scattering intensity and correlate it to the particle size, is not that tough. So the problem starts when your particle starts to become larger. So the first deviation is actually not on here. You start to, if you would see this as a peanut, your peanut will start to get distorted. And the first distortion would be the biscattering. And then if the particle is even larger, you get mescattering. And what you'll see is that even the symmetry of this peanut, you squeeze this one a little bit in the middle and the other blob comes bigger. For larger particles even, you get a completely different scattering profile, which means that you have to know what the shape of your particle starts to become and how large it is in order to correlate your scattering profile to an actual size. And that's not always easy. So what techniques are used then, scattering-wise, to measure these things? Well, I don't want you to remember this equation. The only thing what I want to show you here is that for a single particle, the intensity of the scattered light correlates with the diameter of the particle to the power 6. Now this becomes really important later on for dynamic light scattering. And I'll come back to this diameter to the power 6 a little bit later. Now for a single molecule, the scattering intensity is different than with respect to a particle. So this is Rayleigh scattering, only valid for very small particles. So what I wanted to show you here at mescattering is that mescattering is very complex. So when particles become larger or when the shape changes, you get a way more tough scattering profile. So you'll see here that for large particles, you see a lot of bands and these intensity profiles start to change. But if your particle is not a sphere, so for example, you've got like a square or a pentagon or a dodecagon or just a blob, basically, you get completely different intensity profiles. And they're not even symmetrical. So this flock thing is pretty random. And then from that scattering profile in the machine that you use, so typically for small particles you can use either dynamic or static light scattering, and for larger particles you use equipment like a mastersizer from Malvern. In the equipment there are mathematical procedures to calculate this back to a size. But in order to do that, you need to know a little bit about the shape of these particular things to get the number right. So one of the things for small stuff, and with small stuff I mean gravity-free, we can go back to what we've learned. So we talked about Stokes-Einstein equation, so that the diffusion coefficient was basically related to the thermal energy. So Boltzmann constant times temperature divided by 6 times pi times the viscosity of the medium times the radius of the particle. This only holds for a sphere, right? And typically what you do is you use, there's a number of manufacturers. So the picture here at the top is a Malvern nanosizer in this particular case. And what you do is that you disperse your particles inside a cuvette, and you hit it with a laser beam, so as depicted over here. And as a result of that, you get a scattering profile. So the scattering profile, one of the pictures here is given here on this particular side. And then what you basically do is you kind of take pictures in different time profiles. So I'll go through it a little bit to explain you how you basically go from this picture to an average size. So how does it work? Well, obviously there's lots of particles in this particular thing. So, and obviously all these particles come in at a different angle. So if your light comes in, you get, well, the bottom particle, the light beam hits the particle quicker than the particle at the top. And therefore, if the light has a certain wavelength, obviously, if you bend over, you get here an interference pattern. So you get more intense regions and less intense regions. So now, depending on the intensity, we set the intensity correlated to the power of 6 with the particles. So large particles have got quite a large amplitude of interference patterns, whereas smaller particles, you see here in this intensity profile, have got a way lesser scattering over there. So what the equipment basically does is it measures this profile, and then it correlates it with a certain amount of time. So on this axis, it's a bit difficult to see because it's a small picture. So you go time 10 to the power minus 7 seconds to a region that you've got like 10 seconds, 100 seconds, and even further. You basically take a picture, and then a certain time interval later, you take another picture, and you compare the two pictures with each other. So it's like a correlator profile. And if these pictures are the same, then obviously that is one, the same picture. And if the picture is completely different, they don't look like each other anymore, and it drops all the way to 0 in that particular case. So how does it work? Well, here you see the same thing. So you have this intensity profile, and you have this delay time between two different pictures, and you compare, you know, if there's no movement at all, then you have perfect correlation and you get 1. And if it's moved completely to a different domain, there's no correlation anymore and you drop to 0. So, and obviously what the correlator does, it increases this time interval from very small intervals to slightly larger, 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 larger. So what do you get? So you'll get here these pictures here that this just drops down. So you'll get good correlation. So here you see large particles, and you see that large particles, which move slower, yeah, because it's 1 over r, it takes a longer time for this curve to drop down. So small particles drop down on a way shorter time interval. And you can see already here that on the basis of that, potentially you can get a diffusion coefficient out of this, because this is effectively what you start to measure. Now, obviously, you can also see here in this particular case if you have a bit of a mess in there. So if some of the particles would be coagulated, so you have larger clumps in it, then you will have two different time intervals. So you see small particles coming down first, and you see a plateau level, and then the other particles drop down later. And then with DLS, you're in big trouble if that would happen. So now, in the computer, the problem is you measure the intensity profile from the laser beam, which is not the same as the profile you need that Einstein was talking about, because that's an electric field correlation function. So inside the mathematical procedure, those two are linked to each other. And they're linked to each other basically that the intensity profile, what you measure, equals 1 plus a Gaussian correction factor times the profile that you need to the power 2. So you can interconvert these two. And that's what happens here. So you have, you do the one that you measure minus 1 is a Gaussian term plus then the function that you need in order to link it together. So again, I don't want you to remember these equations. I just want you to kind of get an idea where it comes from. So basically what you do in the end, you have e to the power a term over there, which is multiplied with tau, which is this time interval. And if you take that term and isolate it, you get the diffusion coefficient times the square of the scattered wave vector. The scattered wave vector you know, because what you need to know is the refractive index of the solvent, so you can look it up if it's water. Yeah. You need to know the scattering angle, which means the angle at which you have your detector, which is known. And you need to know the wavelength of the laser, which is also known. Yeah? So as a result of that, you know Q, you fit and you get the expression here. So then you can calculate D, and D is the diffusion coefficient that you want. If you have D, you put it in the Stokes-Einstein equation, and you have the radius of the particle. So that's what DLS does. So here you see some pictures. And I told you already that, so here you clearly see what the influence of the intensity to the power 6 is. So what DLS does, it measures the intensity profile. So you'll see here in this picture, you have a little bit of intensity at about 10, 15 nanometer, and you see some pictures here on the logarithmic scale about 200 nanometer. Yeah? And if you go from intensity to volume, so you go from diameter to the power 6 to diameter to the power 3, you divide by diameter to the power 3, suddenly you see per volume you have way more small ones than large ones. If you then do it per number, again you divide by d to the power 3, you effectively have only small ones. So the top picture is the picture that gets plotted, and it's the average that the machine will tell you that the majority of these particles would be 200 nanometer. Whereas per number, there are way and way and way more small ones than large ones. So if you would do TEM of this, it'll be very difficult to find a large one. Whereas with DLS, it picks out the large one way easier because it scales with the radius to the power 6. So you have to be a little bit careful. So DLS is particularly good if you have a monomodal distribution, pretty narrow, then you know the number you get is the hydrodynamic radius. Because remember also that these particles are in the wet state. Yeah, so if you have some fluffy polymer on the outside, or if you have a double layer with a longer screening length, so a longer Debye length, this particle appears bigger than it is in the dry state. So that's roughly how DLS works. Okay, so what's closely related to that? And that's particle tracking. This is basically takes us all the way back to Jean-Baptiste Perrin, because that's what he did. He used a normal optical microscope to look at large particles, and he monitored the movement and correlated that back to the Einstein-Langevin/Smoluchowski theory. So the only difference with this particular equipment is that you can analyze particles that are smaller than that you could see with a normal light microscope. And the little trick is that they don't look at the particle itself, they look at the scattered light of the particle. So you use dark field microscopy. And with dark field microscopy, you have either light or a laser beam going across the particles. The particles, as we've seen in the previous method, scatter light, and what you see is just a scattered light. So you don't see the particle because you can't see it. Yeah, it's too small, but the light you can follow. So they follow in 2D the movement of this light dot, and as a result of that, you directly put it in the Stokes-Einstein equation, and you get the size distribution. So that works really well. So this is some of the toys we have. Yeah, so you have the laser beam comes in. Here under the microscope eye, it scatters light. So you see like there, you see lots and lots of particles that scatter light, and they're submicron in size. And what you do, you basically make a video clip, and you see how it buzzes around. And then you basically have tracking software that basically at time 0 selects all these dots, and then just follows how it moves. And it uses then the Stokes-Einstein theory to calculate the size distribution. Now, the advantage of using this is that you can have quite polydispersed system. You have large and small particles because you follow them independently. So this technique is better at resolving different particle sizes. However, you got to be careful that this technique typically, in this image, there might be maybe 50 to 100 particles that you follow. So in order to get a good average, you might have to look at different sections and then average it all over each other to take into account like 1,500 or 2,000 particles. Now, this is a very, very simple technique, which is not used very often, but it's very, very useful. And it's called capillary hydrodynamic fractionation. And it's closely related to hydrodynamic chromatography. So it's closely related to GPC in a way. So what have you got in this case? So you have a very, very thin capillary. and you put your particles in there. And we know that in thin capillaries that are empty, you have a lamellar flow profile. So it's called capillary flow there. So the velocity of the liquid is parabolic in 2D. Yeah, which basically means that the liquid in the middle of the capillary moves the fastest, and the liquid on the edges of the capillary effectively sticks. So that's why you get that flow profile. So now if you inject a cocktail of particles, large ones and small ones, the large ones hit the different lamellar fluid streams and therefore get dragged towards the middle, whereas the small ones typically stay where they are. They don't have this drag force that they basically get drawn to the middle. And as a result of that, you separate the different sizes. So large particles come out first, small particles come out last, simply by playing with the flow. And here you see some nice images of this actually happening. So you see particles, again, filmed with dark field, of 26 nanometers coming out last, then a band of 44, and then a band of 110 plus 180. So it's a very elegant way of separating particles of different sizes. Hydrodynamic chromatography is quite related to this, but then you have a packed column similar to GPC, but you can imagine in between the beads, effectively, there's lots of capillaries, and you get the same type of separation. So you get large particles coming out first, small particles coming out last. And you can obviously calibrate this equipment. Now, then you see more and more people playing with microfluidics and making these things even more complex. So you can say, okay, I can have a flow profile in one direction, and I have an other field in the other direction to separate them even further. So in this particular case, you can have gravity playing a role. So for very large particles, they fall down, and the small ones, they don't. So you have a competing effect between those two things. So you have your parabolic flow profile, which puts the larger ones in the middle. But if you have a stronger field at the top, you push the large ones down, and the smaller ones stay in the middle. So you can play with that. But then obviously you can think of different fields, right? You can have an electronic field or electric field. So then the charged particles you can either whack down or up, and the non-charged ones stay nicely in the flow profile. So a lot of people are playing with this for diagnostic kits to see whether they can come up with better ways of separating particles of different characteristics. Okay, so coming back to this gravity. Now gravity, G-force, is determined on planet Earth, but obviously you can speed this up if you want to by centrifugational forces. So this particular equipment does that. So it's a disc centrifuge, and what you have is a plastic disc in a way with a gap in the middle where you can put liquid in. And basically what you do is you spin the disc really fast, up to 24,000 rounds per minute. So you have a pretty high G-force, and then you inject in the middle, if the particles are heavier than the liquid, you inject your sample, and then obviously the particles move towards the outside as a result of the gravitational force. And then somewhere so on the edge here, you have a laser beam, and the laser beam basically measures turbidity. So if particles come by, they scatter, which means turbidity goes up, and therefore it detects that, and as a result of gravitational force, you can separate particles. So you can separate particles on size, but also on shape, because rod-like particles have a different way of being exposed to a gravitational field than spherical particles have. So it's quite a nice toy, and you can separate, well, particles, silica particles of 20 nanometer is fine. Gold works pretty well down to 5. Obviously, the density difference is really important, right? If there's a density match, you won't separate anything at all. If the particles are lighter, you use the inverse. You inject the particles on the outside, and then they move towards the middle. So here you see a nice little application of this. So we studied Pickering emulsion polymerization, so we wanted particles stabilized by small nanoparticles of silica. And in that recipe, it was very, very important that we knew how many small particles were present. Because obviously, latex particles are growing. Because they grow, the interfacial area increases. And if you want to have stability there, you want to decorate the full surface area with particles. Now, if you run out of particles too quickly, say at 70% conversion, and your latex is still growing, you'll end up with a hydrophobic surface where there are no particles present, system becomes unstable, and they bump into each other. You get coagulation. And that's what you see on the picture on the left. You get limited coagulation. So 2 or 3 particles bump into each other. The little ones rearrange themselves over the surface, and you get a bit of a popcorn type of structure. Now, if you added more particles to this, you'll end up with a really nice spherical armored polymer latex in this case. So it's very important that you know how many particles are present, and for that, this centrifugation is perfect, because this centrifugation is very good at separating particles of different size. So what we did was just made a calibration curve of small particles only, so we can calculate the concentration in the water phase, and you basically follow that as function of time. So in this case, we figured out that at 65% conversion, there were no particles left in the water phase, which means we had to add more. And the only way to do that, or one of the few ways to do that, is to monitor it with techniques like this. So very useful. Okay, so that's scattering and tracking and centrifugational separations. So what about, you know, more advanced, well, more expensive, I would say, not more advanced, more expensive toys? So one of the toys is scanning electron microscopy. Now, you may have seen this already or not, so there's some pictures later of this particular equipment. But basically what you do is you image with an electron gun, and there's a few lenses here that basically make sure that you can get your image sharp. And typically the resolution of a field emission SEM on a good day takes you down to about 10 nanometer, I would say. So smaller objects you won't be able to see. And what's really important is that the specimen is conducting. So you either coat your sample with a conducting material, so use plasma sputter gold over it, or platinum or palladium, or a thin carbon film, or alternatively you put a very, very thin sample on a silicon wafer, which is conducting, and then you are able to image as well. Because obviously those electrons have to be able to move away, otherwise you charge your sample. Now, and then whatever comes off, so your secondary electrons go to the photomultiplier, and that gives you the picture. So here you see a typical SEM picture of some work from our group, which are, well, Janus type anisotropic particles. So now this equipment you can use also in a cryo mode, which means you can look at soft materials, because you can imagine if you hit a sample with an electron beam, it can melt. So normal SEM works only for hard matter. If you want to analyze soft matter, you have to operate on a cryo mode. So this is the SEM that we have here in the new mass building. So you see, this is basically your analysis chamber over here. This is the cryo prep unit on the side, on the right-hand side. And on the top left, you have a detector, which is called the EDAX detector. And an EDAX detector can do elemental analysis. So not only can you take a picture, you can also see what elements this sample has been made of. So it's quite useful. So how does cryo work? Well, typically, your sample goes in this little hollow rivet over here. So it's a little bit fiddly. So you put a tiny liquid drop inside this little copper tube. And then that little copper tube gets placed inside this little holder, so over here in the middle, and you can screw it tight so it doesn't fall off. And then the next step is that this holder gets placed on a long rod, so which is basically the rod that takes it into the SEM system. And then you have to freeze it. So what we do is that we fill up these compartments with slush nitrogen, which basically is liquid nitrogen, but then we cool further down. So you'll get a mixture between liquid and solid, and the temperature of that is even slightly lower. And you dunk your sample in there, so you freeze it very fast. And then as a result of that, whilst it's frozen, you transfer it on the side into this cryo prep chamber. And when it's in the side, on the side, you have your sample, and imagine there's lots of ice, and ice is not what you would like to see. Yeah. So if you have a very, very say 5% the dispersion of particles in ice, 95% ice. So you're basically looking for a needle in a haystack. So what we do is like we cut the sample with a knife, fracture it, and then sublime a bit of the ice away, which you can do because like this chamber is in vacuum and sublimation happens above -90. So you can control the temperature of your sample, sublime some ice away, and then what you have to do is you have to coat it because it has to be conducting. So there's a spotter coater inside the prep chamber, and then it moves all the way into the main chamber, and then the temperature drops to about -140 degrees Celsius, and that's where we hit it with the electron beam, and then we can take a picture. And then you can take pictures like this, for example. So this is a picture of a particle stabilized foam. So these are bubbles, air bubbles in ice, and the air bubbles are stabilized by particles in this case. So if you zoom in, here you see a little bit already. You see here that there's particles everywhere. This is clean ice on the side. And you zoom in more. So here you see nicely the particles lying on the air-liquid interface. And here you see the ice. And there's little dots here. You might think maybe those are smaller particles, but that's ice that recrystallizes. Because obviously there's some humidity in the chamber. There's a gold finger on top, but obviously if you hit this with the electron beam, ice will start to sublime and it recondenses here. So if you wait longer, you see these little things go. If you're not sure whether that's a particle or an artifact, you just zoom in with the electron beam, and if it disappears, it was an artifact. So it's a bit fiddly, but you can make really nice pictures. So here you see the pictures that we used with these decorated vesicles. So here, these were sputtered. So what you basically see in order to visualize these, the conducting layer, so the metal layer, is this these broken bits around there. So all the ice is sublimed away, and this metal blanket obviously drops over it, and you see it fractures around these vesicles, and these vesicles are beautifully decorated with polystyrene particles. So without cryo-SEM, you cannot make pictures like this. It's impossible. So it's a very, very useful technique to have. Here you see another picture of that. Lots of vesicles that are decorated with two different types of particles, like large ones and small ones. So what other things you can do with it? So this was the first paper, what we did with this cryo-SEM, and it was a little bit of an accident, really. So we used it basically to make a gas sensor. So imagine you have a dispersion in water of particles. And if you freeze the ice, so you get ice crystals formed, and all other stuff that's not ice stays into the liquid region. So basically your volume fraction of liquid drops and drops and drops. And if you hit 64%, you jam, and you'll end up with a solid. End result is you'll get a mesh embedded in ice crystals. So, and this actually is an old technology that people use to make your bed mattress, right? So you have this foam, in this particular case it's a styrene butadiene type of latex. You cast it over a template, and then the big holes are as a result of the template. If you look carefully, these holes don't match this template, but I couldn't find another picture. And the small microscopic holes are caused by ice crystals. So it's a nice, interesting concept, patented in 1947. So what can you do? You can say, okay, I'm going to use 3 different types of particles. I'm going to play with a few different things. I have conducting carbon black, I have a soft polymeric latex, and I have small hard nanoparticles. And then I freeze the stuff. And what do you get then? And then you look with cryo-SEM to see what you've got. Now, here you see a soft latex, and there's no small nanoparticles present. So what you get, you freeze the system, and then when you obviously heat it up, it just melts, and it just looks like cheese, and if you put the electron beam on it, it gets worse and worse and worse. So if you, however, add these small particles to it, you get beautiful, the structure, the reciprocal structure. So whatever is gone is sublimed ice, it's gone, so it holds now. and then you'll end up with this really nice foam, similar to your bed mattress, only on a smaller scale. And then if you zoom in further, here, you clearly see that you have an enrichment of the small particles on the outside, because they can be closer to the ice crystal, excluded volume effect. And on the inside, you have a composite mesh of the small ones, the soft material, and the conducting material. Now, if you expose this material to vapor, organic vapor, then the soft polymer will swell, which means the conducting parts move further away from each other, which means resistance goes up, so, and the other way, vice versa, so you can use it as a sensor. So here you see sensor number 1 in the lab. You get a piece of foam, 2 little wires, a bit of plastic tubing, a bit of blue tack, and a drop of toluene to check whether it works. And it works really well. And then you integrate it on a printed circuit board. And then you get, so this is version 2, a bit of foam glued together with a bit of silver paste on a little chip. And then there's your gas sensor. It works really well. And now obviously you can further develop this by changing the soft material, so you can get a specific sensor for certain vapors. So, and it works very fast, and you need a tiny, tiny amount of material for this. Okay, so that was SEM. So let's move to TEM. And TEM is a slightly bigger machine. This picture here is one of the smaller ones, actually. We have a huge one now with subatomic resolution in physics. And the difference now is that it says already, the other one was scanning electrons, so you basically scatter off, and this one goes entirely through the sample, which basically means that your sample has to be really thin. So roughly, if your sample is thicker than 500 nanometer, forget it. It's just black, right? You won't see anything. If your sample is big and crystalline, the electron gun scatters everywhere. You won't see anything. So you have to have really, really small samples, or you slice it. So you can salami slice it. If you have a big sample, you can embed it in a resin and cut a slice of 100 nanometer thick, put that on your SEM grid, on your grid, and put it in this machine. Alternatively, very recently we've got a FIB SEM, so you can use an ion beam in order to make the same little slice and use it as a TEM sample. So that sample is tiny compared to the a conventional SEM sample. You put it in here, and you basically blast your electrons right through it, and what you see is, well, something like this. So this is a rather bizarre TEM sample of a polydispersed system. And then typically, if you want to have particle size distribution out of this, you have to have about 1,500 particles. Now, there are 2 ways of counting 1,500 particles. One is you ask one of your students to count them one by one and measure it. And this is the way that it was done in the 1980s and the 1990s. Or now, luckily, there is some software. So if you have your contrast high enough between particle and non-particle, you automatically can filter it to this, and it does the trick for you. And you have it done in about, well, you know, in say 10, 15 minutes. If you do it manually, you're happy for 2 days, I would say. So, and then you get a nice particle size distribution. Obviously, with TEM, you can see a lot more detail. So here you see a cryo TEM picture. So with TEM, we can also measure in a cryogenic mode, but then we take a sample on a tiny little carbon grid, and then we freeze it even faster. We freeze it in liquid ethane, because now the ice has to be amorphous, because you go all the way through the sample. So if the ice is crystalline, the electron beam will scatter, and you won't see anything. So we have to freeze so fast that we freeze faster than the ice can crystallize, so that's why we use liquid ethane. And temperatures, well, typically you have to stay below minus 135 degrees Celsius of water, because that's the glass transition temperature of ice. So below there, you end up with amorphous ice. And then you see these little dots in here, and they're just either ice bits or ethane bits that have got incorporated in there. And here you see a particle that has hairs. And you kind of think, so these are polymeric hairs, polymer brushes that row of particles. And then you might say, oh, Stefan, you're talking nonsense, because, you know, the scale bar here says about, what, a bit less than 200 nanometers for the core, and if these are brushes, then I can see individual polymer brushes, which obviously would not be possible on this particular length scale, because one chain would be what 0.1, 0.2 nanometer. Now the funny bit of this particular sample is the ice is really thin and it partially crystallized, and you can see that because you have these streaks in the ice. And well, this is almost like what I want to call the wet hair effect. Because the ice crystallizes, it pushes the polymer chains together. So you see a bundle, like you have with wet hair. You have a bundle of them, and because it's a bundle, you can see them. If they're all nicely dispersed, you won't be able to see them, and in that particular case, you will be able to see them. So here you see clearly the core, and you can roughly guess how big this hairy layer is. So if you would take the same sample and you put it in the dynamic light scattering machine, what you'll measure, the diameter, will be the total diameter, the hydrodynamic diameter. So all the hair stretched out. So the big diameter is what you measure with DLS. With TEM, that big diameter should roughly agree, but you also have the core diameter of the particle. So that's very, very interesting. Okay, so what else can you do with cryo? So here you see some samples which were very difficult to image. You would not be able to see this with conventional SEM or with conventional TEM. It's tough. They're very, very soft particles, and we decorated them with lapunite clay discs. Now these discs are 25 nanometer roughly by 1. Yeah, so you might argue that, okay, that's a very, very thin slice. Yeah, and whatever depends the the contrast of the image gets determined by obviously how heavy your elements are. Heavy elements scatter better than light elements, so you get a darker dot. So if the clay platelet lies flat, you're literally going through 1 nanometer, and that's difficult to see. But if the clay platelet stands upright, you're going through 25 nanometers. And the clay platelet is composed of, well, silicon dioxide, 2 layers of silicon dioxide with some metal atoms in between. So if it stands upright, you can quite clearly see it. And that's why in all of these images, you see the clay platelets really clear when at the edges here, where they stand like this, of the spherical particles, and when they're dispersed like this through the matrix. Now, the important thing with this particular sample was, this again was a type of Pickering emulsion polymerization system in which we wanted the clay platelets to be on the surface of the particles, but you have to have proof for that. And these clay platelets, they're a pain to separate by any other technique. So because they stack a bit like cards, it's impossible to separate this with disk centrifugation. So the only way to check whether they're on or off is cryo-temp. So what you see here on the left-hand side, PMMA with butyl acrylate, you can clearly see that the clay platelets are beautifully decorated around these soft particles. And you can even see the particles are soft because the platelet is hard and it distorts the particles from being spherical. It's quite nice. Styrene butyl acrylate also works quite nicely. You see the clay platelets beautiful around. But if you then change butyl acrylate for something more hydrophobic, ethyl hexyl acrylate, there is no affinity for the platelet to lie on the surface. So now what you end up with is a bunch of almost like naked particles. Sometimes there's a platelet attached to it, and a lot of clay left in the water. So, and this would give you, if you would turn this into a material, a lot of bad properties. Because when you would film form this, and we talked about film formation yesterday, all the clay would just clump together and you get big cracks. Whereas in these 2 cases on the left, you get beautiful honeycomb type of structure, which is a nice material to play with. So in order to solve this, yeah, if this particle would be too hydrophobic, you can add a little bit of a co-monomer that's hydrophilic. So if you add a tiny amount of methyl acrylate, methacrylic acid to this emulsion polymerization recipe, then all the platelets are around the particle. So you've solved your problem. So cryo-temp, in this particular case, very, very useful to look at. And here you see just another image showing the same thing. So you can beautifully see that these clay platelets decorate very nicely over the particles. Yeah, if you're really cynical, you can say, well, maybe they're only here on the outside and there's nothing lying flat, but that would be kind of weird. And actually, you can prove that that's not the case. We haven't done that with this sample because you can tilt your sample. So you can, in the cryo stage, you can take a sample on a different angle. So, and if you do that for enough angles, you can get a 3D representation back. And obviously, if you tilt the angle, you get a different clay platelet. So that would definitely nail it, that they're all basically beautifully arranged around these particles. Okay. Yeah, so hopefully I've given you a little bit of an overview what techniques are available. There's a few more techniques available, but these are the main basic ones to look at colloidal matter. So imaging, SEM, TM, vital, especially the cryo ones for soft matter, and then the more traditional ones like, well, dynamic light scattering, static light scattering, Mie scattering, and particle tracking.